All right, we're going to dig a little deeper now into change processes, and we're going to introduce a way that we can visualize those processes using pressure volume diagrams or PV diagrams. Let me first talk about a couple of general types of change processes that we're going to be concerned with. Okay, the first of these I'm going to refer to as an irreversible change. Now, what might that be? Well, for example, if I have a container that has a gas in a vacuum, so let's say here's my container that contains a gas, and it's got a valve that I can turn on and off, and it's connected to a chamber that has a vacuum. I think it's pretty obvious that if I open that valve, the gas is going to expand into that chamber, and there's not much I can do about it. It is a fast, spontaneous change, and it is in fact irreversible. Now, I say it's irreversible. We can imagine that the gas isn't all of a sudden going to decide to go from this chamber into which it has expanded back into this bulb and all be there again. No, once it's expanded in there, it's there. So this is why we call them irreversible processes. We're going to be actually concerned a lot with spontaneous processes in a couple of modules, but for now we want to try to get a handle on energy changes that are occurring, and it turns out that these are particularly difficult processes to get that. Now, one of the things that one might indicate, for example, is that if the external pressure outside of a system is greater than the internal pressure, and we open up the possibility of exchanging heat or work, this would result in a compression. In other words, the outside pressure is higher, so it's pressing in on the system, it's going to compress the system. The change in volume is going to be less than zero, so it's going to compress the system. This is a case where work will be performed against the internal pressure. Okay, this is the pressure of reference that we need to care about. If, on the other hand, the external pressure were less than the internal pressure, then the opposite case would happen. We'd have expansion of the system. The change in volume would be greater than zero, and the work would be against the pressure P external. All right. Okay, so these are cases where we've got irreversible expansion or compression happening because of pressure differences between the system and its surroundings. But what would happen if, for example, we had a particular case where the external pressure was equal to the internal pressure? What happens then? Well, we would call this, first of all, an equilibrium. There is no net force that causes a change in either direction. This means that whatever change might happen would happen slowly, and it could be reversed if these things are very close. So we're going to define this as conditions under which it might be possible to have a reversible process. So that's the second type of process that we should worry about, and that is a reversible process. And I'll say right off the bat that this is an artificial arrangement. I mean, there are ways that you can set things up so that change happens very slowly and it's effectively at equilibrium the whole time. But this is not going to be the sort of change that you would see in nature. Nature is going to be an irreversible, spontaneous change. The other thing about this is that for a reversible change, the system remains at equilibrium throughout the change. So this makes it possible to track that change in what's going on. Now, a lot of these reversible systems, we use them in thermodynamics not because they are indicative of exactly what happens in the real world, but because if we can use reversible processes to go from an initial state to a final state and measure a change in a state function, that change in the state function is the same whether the process was reversible or irreversible. So in other words, these are basically describing two different types of paths. Okay, the path could be a reversible path or it could be an irreversible path. But whatever it is, it's a different way of going from an initial state to a final state. And one of those we can actually measure carefully, that is this one. We can measure carefully. The other one may not be possible to measure state functions. Now, we're going to be interested in various kinds of changes that involve constraints. And we've seen one of these already in the previous video when we talked about bringing two things into thermal contact but keeping the volume constant. So one of the ways that we can impose a constraint is to have a constant volume. All right, now I'm going to go through the different things we can hold constant, and then I'll tell you what they're called. Another thing that we could have done is we could have a process that has a constant pressure or a constant temperature. All right, these are also constraints that we could impose upon a change process. A final kind of change that I'll talk about is, there are more than just these four, but we're going to talk some about adiabatic changes. These are changes that basically impose no heat exchange. So in other words, the incremental change in heat for an adiabatic process is equal to 0. All right, all of these others involve physical property changes that are held constant, and we're going to have a lot to say about all four of these in various future lessons. Now let me put a label on these so that we can use some special language. A change that involves a constant volume is called an isochoric change, based on Greek roots. A change that involves constant pressure is called an isobaric change. And you might recognize bar as being the same root as used in barometer. A barometer is something that measures pressure. So isobaric means same pressure or constant pressure. Constant temperature, this one will be also more familiar, we would call an isothermal change. That is, the temperature is not changing. Okay, now in the case of a constant volume, this means that V is staying the same throughout the process, theoretically. Likewise, a constant pressure process would be pressure is the same throughout the process, and temperature would be temperature is the same throughout the process. Now, these are particularly important to specify that they're throughout the process when we're talking about path functions. So in other words, these are going to be important when we want to measure something like the heat or the work that's involved in a change process. But if it's a state function that we're worrying about, if it's something like the internal energy or the change in internal energy, these will not care if it's actually the same throughout the process. All it will care is that it's the same at the beginning and the end of the process. All right, now I want to talk a little bit about PV diagrams. These are a special way we have of tracking these things. And I will also say that PV diagrams are especially useful when we're talking about reversible processes, because a reversible process allows us to actually specify a path graphically on a PV diagram. All right, so what is a PV diagram? Well, a PV diagram is one where we're going to draw a graph in which we graph pressure on the vertical axis and volume on the horizontal axis. And so each point in this graph is going to represent a separate pressure and volume, and these can change then throughout. So I could actually label this as point 1, and maybe I'd have another pressure volume point that would be here, that would be pressure and volume 2. Now, one reason that PV diagrams are useful is that they often enable us to determine other things too. For example, it is not uncommon to let the amount of substance in a system remain constant. We'll talk eventually about things where this changes, but at least for the first couple of modules, this is always going to be the case in our systems. So what that means is that we have an equation of state that relates the other variables, pressure, volume, and temperature. N is constant, so I'm going to put it sort of separate a little bit with a semicolon. But our equation of state, which I'll remind you looks something like this, will say that if I know where the pressure and volume is, I can always find the temperature. So for example, for an ideal gas, if I know the pressure and the volume, and I know that this is equal to nRT, but n is constant, then I can always solve for the temperature. It's just going to be PV divided by nR. So I can always determine what this is. So each of the points here in the pressure volume diagram, in the PV diagram, actually tells me about the entire state of the system, and that's why these things are useful. All right, so let's look at a few examples here, and what I want to do is talk about how system changes might be drawn here. So we're going to focus on system changes, and in particular these are going to be reversible system changes. So I've drawn on the previous page a picture of a PV diagram that looks something like this. Probably should have put my axes up there to begin with. And we're going to be moving from an initial point P1, V1 to a final point P2, V2. Now the whole point of the PV diagram is that I could just have a process that does this. State functions like the internal energy will always represent the same quantity no matter how I go from this first point P1, V1 to the second point P2, V2. But that doesn't mean that's how the process had to go. The process could have followed this path to get there, or it could have gone this way to get there. Okay, however it goes from here to here won't affect the internal energy, but it will affect the heat and the work that are involved in that process. And that's why they are called path functions, because these are different paths that took me from an initial state here to a final state here. All right, so what can some of these initial and final states paths look like? Okay, well, let's look at those different change processes with constraints. So remember, an isochoric process was constant volume. Constant volume. So that means if I start here at this point, constant volume is always the horizontal axis. So that means I have to go straight up vertically to my final point. So this would be an isochoric process, would be just a vertical line on this. What about isobaric change? Remember, that was constant pressure. All right, so now if I start here and I go to here, I would have pressure is constant because it's the vertical axis, volume is the horizontal axis. So in the first case, I have this is going to result in a change in pressure. In this case, I'm going to have a change in volume, but no change in pressure. The pressure listed over here is constant. Now I've drawn this as an expansion because the delta V is positive, but I could have also drawn this for a compression where the delta V is negative. All right, so you can represent both of these things on a PV diagram. Okay, what about isothermal? That's the third constraint. Okay, isothermal, remember, was constant temperature. How does that look on this? Okay, well, to see this, we're going to have to rely on our ideal gas equation of state. So we're assuming that this is an ideal gas now. And remember, that's equal to nRT, but this is constant. And in an isothermal process, so is temperature. So in effect, PV equals constant. So what does that graph look like? Well, if I start here, that graph might look like this. It kind of curves down. It looks like a hyperbola. So here is my initial point, and here is my final point. All right, so this would be an isothermal change and how it looks in this PV diagram for an ideal gas. Okay, for a non-ideal gas, it may look a little bit different. We're actually going to be talking about isothermal changes a little bit later and see how we can, what we can learn from looking at the shape of this. Now, I've talked a little bit about how we might represent these paths in a PV diagram, but how do we calculate things? Well, remember we wrote that work was equal to minus P dV, the incremental change in work. So if we actually want to calculate work, we have to do an integration from the initial point to the final point, and it's going to be the pressure times the change in volume. Now I've explicitly written the pressure here as a function of volume. Okay, as the vertical axis in each of these graphs, we are seeing here that these things, these paths, tell us what the pressure as a function of volume is. Whoops. Let's draw that P as a fraction of volume. Here, P as a function of volume. P as a function of volume is a constant over the volume in the isothermal case. It's a constant as a function of volume in the isobaric case. So it's just a horizontal line. Okay, so if we're doing this, what does this integral represent? Well, I hope one of the things that you learned in calculus was that an integral of a function is basically telling you what is the area under the curve. So what I'm really getting from doing this evaluation of the work is I am measuring an area. And the magnitude of that measurement is going to tell me what the magnitude of the work is. Now, I've left something out of this equation. I've left out that minus sign. So what that tells us is if I have a process, I need to multiply that area by -1 in order to get the work. And this is going to affect how we interpret different things in the diagram. Well, let's go to another page and see how we might draw this. So work on a PV diagram and how this would be represented. Okay, so work is equal to the magnitude of the area under the PV curve. P is a function of volume. So let's say, for example, we have an isobaric process and it's an expansion that goes from point 1 to point 2. All right, so P is equal to constant. So this is isobaric. If I did that integral for the work, remember the integral is -1 to 2 of pressure times dV. The pressure is constant, so in this case it's going to be minus the pressure times the integral of dV from 1 to 2, which is just minus pressure times V2 minus V1. All right, so what is that in this case? Well, the area under this curve is just this area. So this would be the magnitude of the work. Now, since it has the minus sign out here, and this was an expansion, that means that this is a positive quantity, and this makes it negative. So in fact, it's going to be the negative of this in this particular case. All right, what if instead I had used as a compression? What would it then be? Well, now it would be the area under the curve and it would be positive. So what this is telling us is if we are moving from left to right, the work is the negative area, and if we are moving from right to left, the work is the positive area under the curve. All right, but this is going to be true for any path that we might follow from an initial point to a final point. So if my initial point is here and my final point is here, and actually I've screwed this up a little bit by making this such a complicated diagram, but for this part of the curve up to here, it'll be the negative area under this part of the curve, and now it will be this part of the curve here and this part of the curve here, but it won't include this region in here because we were going from right to left. So this is a case where it's really the area inside this curve and the horizontal axis. So in general, what we'll find is that if we make some path, and even if we, let's say we make it a path that comes around in a total circle, well, this part of the path will count as a negative work, but it will go all the way down to the bottom. And then this part of the curve will count as positive work, so it will cancel that out. So when these two cancel each other out, we find that actually the network is equal to the area inside this, and it will end up being a negative area because the higher curve was the one going from left to right. I probably told you more than I needed to tell you at this point, but what we can see is these PV diagrams are remarkably useful when we want to talk about different kinds of processes that are reversible, so that we can describe the path that connects the initial point to the final point.